Hello everyone. Today, we will study the basics of transformer parallel operation. Basic knowledge of transformer parallel operation. This lesson requires mastering the following aspects. To master this part of the content, 1. Understanding the definition of transformer parallel operation. 2. Understanding the advantages of transformer parallel operation. 3. Understanding the ideal conditions for transformer parallel operation. 4. Understanding the actual conditions for transformer parallel operation. The capacity of modern power plants and substations is increasing. One transformer often cannot bear the entire load. Multi-pole transformers are usually operated in parallel. So, what is transformer parallel operation? Parallel operation refers to the operation of two or more transformers, where their primary and secondary windings are connected to a common bus, simultaneously providing power to the load. This method of operation is called transformer parallel operation. This method of operation is called transformer parallel operation. As shown in the diagram, please see Figure A. This is the structural schematic of two three-phase transformers in parallel operation. The primary side of the first transformer and the primary side of the second transformer's phase A are connected to the phase A bus. The primary side of the first transformer and the primary side of the second transformer's phase B are connected to the phase B bus. The same goes for phase C. The connection rules for the secondary sides of the two transformers are the same as the primary sides. That is, the starting terminals of the same phase coils of each transformer are connected to the corresponding same phase bus. This is parallel operation. The function of each phase bus is to gather and distribute electrical energy. Next, please see Figure B. This is a wiring schematic of two single-phase transformers in parallel operation. This diagram also applies to any phase in the parallel operation of three-phase transformers. Also, note in the diagram that the dashed lines, whether on the primary or secondary side, show that both transformers form a closed path through the bus. At this point, think about the following questions. 1. When a single transformer operates without load, is there any current flowing through the secondary winding? 2. If there is a certain voltage difference between the secondary windings of two transformers running in parallel, and the transformers are still operating without load, is there any current flowing through the closed loop? So, why do transformers run in parallel? Let's analyze by taking two single-phase transformers running in parallel as an example. Assume that each transformer running in parallel has a capacity of 200 kVA. At the same time, these two transformers supply power to two enterprise users, each with a power demand of 100 kVA. Normally, both transformers supply power to the load simultaneously. Let's discuss the following scenarios. 1. If one day one transformer needs to be shut down for maintenance, then the entire 200 kVA load should be supplied by the other transformer. Compared to non-parallel operation, this improves the reliability of power supply. 2. For the power-using unit, there are times when equipment needs to be shut down for maintenance. If one day one user needs to shut down for maintenance, and there is only a 100 kVA load, then, according to the load change, the number of transformers in operation can be adjusted. That is, stop one transformer to reduce losses, thereby improving efficiency and ensuring economic operation. 3. As the power demand of users gradually increases over time, if transformers do not operate in parallel, then the purchase of transformers must consider the development 10 or even 20 years into the future, and the initial capacity needs to be large. However, in the early stage of factory construction, the actual power consumption is not large. 1. This makes it difficult for the user's investment to be recovered. 2. Reduces the operational efficiency of the transformers. If transformers operate in parallel, the unit can increase the capacity and number of transformers in stages according to the growth in power consumption to reduce the reserve capacity and initial investment of transformers. Based on the above analysis, we can conclude the advantages of transformer parallel operation as follows. 1. Improve power supply reliability. 2. Improve operational efficiency. 3. Reduce reserve capacity and initial investment. Next, let's analyze the conditions for transformer parallel operation. The ideal conditions for transformer parallel cooperation are 1. When no load, there should be no circulating current in the primary and secondary windings of each transformer. Only the primary side has no load current. So, what is circulating current? As previously mentioned, as shown in the right diagram, whether on the primary or secondary side, the two transformers in parallel form a closed path through the base. As shown by the dashed lines, when the transformer operates without load, the current flowing around the secondary side of the parallel operation is called circulating current. When operating without load, circulating current exists, and it will not disappear when the transformer is loaded. Therefore, its existence occupies the transformer's output capacity. According to the magnetic balance equation, when there is a circulating current on the secondary side, there is also circulating current on the primary side. The relationship between the circulating currents on the primary and secondary sides of the transformer is the circulating current on the primary side, IC1, is equal to the circulating current on the secondary side, IC2, divided by K. At this point, please think about the following question. Under what conditions will circulating current appear during transformer operation? 2. When transformers are loaded. The load factors of the transformers should be equal. That is, the loads borne by each transformer should be distributed in proportion to their rated capacities. Transformers with larger capacities should bear more load, thereby ensuring that the transformer capacities are fully utilized. 3. When transformers are loaded, the load current of each transformer should be in phase. In this way, when the secondary side currents of each transformer are certain, the total load current should be maximized, or when the total load current is certain, the currents shed by each transformer are minimized. Based on the ideal conditions for transformer parallel operation, we will further analyze the actual conditions that must be met for transformer parallel operation. If there is circulating current when the transformer operates without load, this means the secondary winding voltages are not equal during parallel operation. There are two reasons for the unequal secondary side voltages. 1. The transformation ratios of the parallel operating transformers are not equal. Unequal transformation ratios cause unequal secondary side voltages during operation, thus generating circulating current. The greater the difference in transformation ratios, the greater the circulating current. Since the rated secondary current of the transformer does not change, the load current that the transformer can bear is reduced. 2. The connection groups of the parallel operating transformers are different. Because the transformers operate in parallel, the primary sides are connected to the same voltage. That is, the primary side voltages are equal. If the connection groups of the two parallel operating transformers are not equal, it means that there is a voltage difference on the secondary sides of the parallel operating transformers. This voltage difference causes a large circulating current. Obviously, parallel operating transformers, if the connection group differs by 1, this is the smallest impact case, and the circulating current in this case can reach about 10 times the rated current, thus burning out the transformer. Therefore, transformers with different connection groups are absolutely not allowed to operate in parallel. Based on the ideal conditions for parallel operating transformers, 2. When transformers are loaded, the load factors of the transformers should be equal. That is, the loads borne by each transformer should be distributed in proportion to their rated capacities. According to the simplified circuit diagram of the transformer, the voltages of the parallel operating transformers should be equal. That is, equal to. This formula indicates that when the load factors of the transformers are equal, the per unit values of the short circuit impedance of the parallel transformers should be equal. This leads to the actual conditions for parallel operating transformers. If the parallel operating transformers distribute the loads in proportion to their capacities, the voltage values of the short circuit impedance of the actual parallel operating transformers must be equal. Based on the ideal conditions for transformer parallel operation. 3. When transformers are loaded, the currents of the transformers should be in phase, thus maximizing the total load current shed, since a low current phasor equals the sum of the phasors of the two transformers' currents. That is, the phasor of I equals the sum of the phasors of, according to the phasor diagram, to maximum the total current, the short circuit impedance angles of the two parallel operating transformers should be equal. Through analysis, the actual conditions for transformer parallel operation are as follows. The rated voltages of the primary and secondary windings of the transformer should be equal. That is, the transformation ratios should be equal. 2. The connection groups of the transformers should be equal. 3. The short circuit voltage, that is, the per unit values of the impedance of the transformers, should be equal. 4. The short circuit impedance angles should also be equal. Among the above 4 conditions, condition 2 is an absolute condition. That is, transformers with different connection groups are absolutely not allowed to operate in parallel. The other 3 conditions are relative conditions. This first condition is, since transformers are generally not fully loaded, so the circulating current should be within a certain range. To prevent the circulating current from being too large and affecting the transformer's output power, it is usually stipulated that the deviation of the transformation ratio of the transformer should not exceed 0.5% of the average value. The third condition is, similarly, the per unit values of the short circuit impedance during operation have certain differences. It is stipulated that the per unit values of the short circuit impedance of parallel operating transformers should not differ by more than 10% of the average value. The condition is, if the short circuit impedance angles do not differ significantly, it does not have much impact on the transformer's output. Therefore, it is stipulated that the short-circuit impedance angles should be between 10 degrees and 20 degrees. In this lesson, we mainly introduce the definition and advantages of transformer parallel operation, as well as the ideal and actual conditions for transformer parallel operation. The actual conditions are derived from the ideal conditions. The relationship is defined such that actual conditions 1 and 2 are to meet ideal condition 1. Actual conditions 3 and 3 correspond to ideal conditions 2 and 3. This correspondence can be better understood through the analysis of transformer parallel operation. Okay, that's all for this lesson. Thank you, everyone.